In this section, let's have a look at what happens when we mix together strong acids and strong bases. So when we have a mixture of a strong acid and a strong base, we call that a neutralization reaction. You might remember that from Chemistry 11 and even from Science 10. And the simple expression or the simple reaction is written below here for a neutralization reaction. When you have a strong acid and a strong base, we create a salt and water. And strong acids, as we know, ionize 100%. So they produce solutions of H+. And the H+ from the acid is what reacts with the hydroxide ion from the base. Strong bases, as you remember, ionize 100% as well. So if you have, for example, an Arrhenius base, which is one that ends in OH, it will ionize 100% and it will produce a solution of hydroxide ions. And each one of those H+ ions and hydroxide ions combine together to give us our water, the H2O. The salt is created from the cation and the anion from the base and the acid, which combine together to give us a salt. Now, in a perfect situation, or in an exact neutralization, we'd have equal amounts of H+ and OH, so that in the end, the water, which is neutral, and the salt, which is neutral, create a solution with a pH of 7, or a neutral solution. And this would happen if our H+ concentration and our OH, or hydroxide ion concentration, were exactly equal. So they balance each other out. Now, whether that resulting solution is neutral, though, depends on how much acid and how much base we start with, or in other words, the relative concentrations of the H+ and the OH-. So if we don't have a situation in which the H+ is exactly equal to the OH-, then we have what we call an inexact neutralization. And in an inexact neutralization, either the H+ is in excess or the hydroxide ion is in excess. And we need to determine which one's in excess, by how much, and then that will determine whether or not the resulting solution is basic or acidic. And we can calculate the exact pH by determining the excess concentration of the ion that's in excess. Let's go ahead and do an example of this. So we have 10 milliliters. In this example, 10 milliliters of 0.1 molar HCl. HCl is a strong acid, so right away I should unpack my question a little bit and think about what I'm given. So I've got a strong acid, okay, and it's added to 90 mils of a 0.1 molar solution of sodium hydroxide. Sodium hydroxide is a strong base. I recognize that it's an Arrhenius base and it ends with OH-, and all of those all of the metal hydroxides are strong bases. So anytime we see a metal cation paired with an OH, okay, we know that that's a strong base and it ionizes 100%. The question is, if we combine these two mixtures of acid and base together, what is the pH of the resulting mixture? So the first thing that we want to do here is that we want to determine whether or not we have H+ in excess or OH- in excess. But to do that, we're going to have to figure out what the concentration of H+ is and the concentration of OH-. Now remember what our neutralization reaction is. I could write it like this. It's HCl, okay, plus sodium hydroxide. It's going to give us water, H2O, plus the salt, sodium chloride. Now, the Cl and the Na in an aqueous solution, the sodium ion, the chloride ion, those are all spectator ions. We can just forget about them for the sense of simplifying this. Okay, if we ignore the spectators and we really write out what's the net ionic equation here, we have H+ hydrogen ion pairing with a hydroxide ion to give us water. That is our neutralization reaction equation. Okay. Now in an exact neutralization, these would be equal, but in an inexact neutralization we might have more of the H+ or more of the hydroxide ion, and that's what we need to find out. Now we know our strong acid is going to ionize 100%, and we can figure out what is the concentration of that acid after the dilution. We can do the same thing for the base. After the dilution, what will be the concentration? And it is important to recognize here that we're mixing, which means we are doing a dilution. So we are going to be looking for the concentration after the 10 mils of acid and the 90 mils of base have been added together for a final volume of 100 mils. So let's go ahead and we're going to do two separate calculations, and what we're looking for here is the H plus calculation after dilution. Okay, after dilution. And we're also going to look for the OH minus concentration after dilution. We'll do that one next. So let's go ahead and start by writing out the reaction equation here for the acid. Now, why would you do this? You might say, well, I can just go ahead and calculate the concentration of HCl, and I know that's equal to the H plus concentration. It's always a good idea just to write out the acid ionization and the base ionization. Just make sure that your acids in a 1-to-1 ratio with the H plus, or if it's not, figure out what is the ratio, and the same thing for the base. Always just good to make sure you know what the ratio is from your acid to your H plus concentration and your base to your OH minus concentration. So here I'm going to go ahead, I'm going to write out my HCl. Okay, ionizes 100%, and it gives me H plus and chloride ion, which I'm not really worried about. I'm really just worried about my HCl. But what I do notice here is that I have a 1-to-1 ratio of acid to H plus my proton. And so that tells me that whatever I calculate for my concentration of HCl is going to be equal to the H plus concentration. So now we can go ahead and do that. So the HCl concentration after dilution. Okay, well, let's see what we've got here. Remember what our calculation is for a dilution. It is C1V1 equals C2V2. And in Hebden in our textbook, it also calls it C initial, volume initial equals concentration final, volume final. Either one of those are totally fine. They mean the same thing. I just like to use 1 and 2. So here we're looking for C2 or C final, and we're going to start with the initial concentration, which is 0.1 molar. Keep my units in my calculations, multiplied by V1. Okay, I'm looking for C2, so C2 is going to be C1V1 over V2. Okay, so V1 initial volume is 10 mils for the acid. Now it's okay to use milliliters here. I don't need to convert to liters. The reason I don't need to convert to liters is because I'm doing a dilution calculation, and as long as I keep the units of volume consistent in the numerator and the denominator, then they will cancel. So I could convert to liters if I wanted to, but it's an extra step I don't need to do. Okay, so in the bottom, volume 2, final volume, is the 10 mils plus the 90 mils, so that's 100 mils. I'll just show all my work here. Okay, so 10 plus 90, and my units are milliliters, so those units of milliliters cancel. And what I have is a dilution of my original concentration. So let's go ahead and do that. 0.1 times 10 divided by 10 plus 90 is 100 mils, and my answer is going to come out to be equal to 0.0100. My units are moles per liter. This is a concentration. And let's keep track of our sig figs. We are allowed to have 1, 2, 3 sig figs. So I'm just going to go ahead and underline those 3 sig figs, which I'm allowed to have. Okay. So I found my concentration of HCl, and because it's in a 1-to-1 ratio, that means the concentration of H plus after dilution is also equal to 0.0100 moles per liter. Okay, now I'm ready to do the exact same thing, but I'm going to find the OH concentration after dilution. So this time I'll be looking at the base and the information that I have about that. 90 mils of 0.1 molar NaOH, and I'm adding 10 mils to it. Okay, so let's go ahead and do the exact same thing here. So now I'm going to find my concentration of OH minus, okay, after the dilution. Okay, so writing out my ionization of my base. So sodium hydroxide gives me sodium ion plus hydroxide ion, and it's 100% ionized, and it's in a 1-to-1 ratio with my hydroxide ion anion here. Okay, so again, I'm going to now find the concentration of NaOH, which is equal to the concentration of OH minus after the dilution. So I need to do a dilution calculation. So it's going to be C1V1 divided by V2, final volume. So I have initial concentration of my sodium hydroxide was 0.1 molar. Both the acid and the base happen to have the same original concentration, times by the initial volume of my base, which was 90 mils. And I'm okay to leave this in milliliters, as I said before. Okay, and I'm going to divide that by the final volume, which is 100 mils. Always really important that we don't forget to add the two volumes together in the bottom. Okay, and then my final concentration, I can do the math, is going to work out to be 0.0900 units or moles per liter. My milliliters have cancelled, and I'm left with a concentration. And that's a decimal place right there. Okay, and I'm allowed 3 sig figs here from this calculation, and I've got my 3 sig figs there, which I'm going to underline. Okay, so I've got my concentration of H plus, my concentration of OH minus, and now we come back to that original neutralization reaction. The H plus and the OH minus come together to form water. So the question is, who is in excess here? And we can write out our amounts underneath, or we could compare them. Okay, and I'm going to write them out underneath. So I've got 0.01 molar for the H plus, and I have 0.0900 moles per liter for the hydroxide. So I can see that my hydroxide is in excess. I have a greater concentration of hydroxide than I do H plus, which means that I'm, in the end, when these are mixed, I'm still going to have some OH minus left over, so this solution is going to be basic. Now the question is, by how much? And we know that all of the 0.01 molar H plus is going to react with an equal amount of OH minus. So the amount in excess is simply going to be the difference. Okay, however much OH minus is left over. And we write this out with a really simple equation that looks like this. Okay, the concentration of our ion in excess, which in this case is OH minus, is going to be equal to however much OH minus we started with, essentially minus how much was reacted, but it's easier here to say we know that it's going to react with the H plus, and so whatever your concentration of H plus is here, and so I'll write, H plus, okay, at the start, because all of that H plus is going to be reacted with an equal amount of OH minus. So this will tell me how much OH minus is left over. So I can go ahead now and I can plug my values in. So at the start I've got 0.0900 moles per liter of my OH minus, and if I subtract the H plus concentration, 0.0100 moles per liter, then I'm left with the excess concentration of OH minus. Okay, and the difference here is going to work out to be equal to 0.08. Now don't forget about our sig figs. We were allowed 3 sig figs for both of our concentrations, and here we're performing a subtraction, so we're using the decimal place rule. Okay, but we're allowed to go up to 1, 2, 3, 4 decimal places, so we've got 0.0800 moles per liter is the concentration of OH minus now in excess. So that's how much OH minus is still floating around in our resulting solution. And I can go one step further now and I can find out what is the pH. But because I have an OH minus concentration, I'm first going to find POH, and then I can go to pH. So the POH is equal to the negative log of the OH minus concentration, which is 0.08 moles per liter. So the POH here is going to be equal to 1.097 when I put it into my calculator. Great. And now pH, as we know, is going to be equal to 14 minus the POH. Remember that pH plus POH added together give us 14. So if I want to find pH when I'm given POH, I can simply move that POH over to the other side, so I subtract it on both sides. So I've got 14 minus the POH, so minus 1.097. It's always really important to be careful with this part of the calculation. Try not to do it too quickly in your head. Sometimes it's a good idea just to write it out, especially if you had a negative POH, because if the value was negative, we'd actually be adding it to the value of 14. So just be a little bit careful that you don't just make a simple error after you've done all this work, right? pH in this case is going to be equal to 12.903. And again, I'm allowed to have here, I'm allowed to have 3 sig figs after the 12, and I'm using the decimal place rule. The 14 is an exact number, so I can ignore it, but I am allowed to have these 3 decimal places after. Okay, and that's my final answer for pH. So this is a basic solution after I mix them together with a resulting pH of 12.903, which is basic.